Hello and welcome to AP Daily for AP Physics C, Electricity and Magnetism. Today we're going to take a look at topic 9.2 for electric potential. This is daily video 4, where in this video we will explore how point charge configurations can yield zero potential energy and or zero electric field. My name is Michelle Strand. I am coming to you as an Einstein Fellow on Capitol Hill in Washington, D.C. So let's do a little warm up here. So when looking at electric field and electric potential, we want to think about a group of 4-point charges labeled here A, B, C, and D. They are on the X and Y axes, and they're all equidistant from the origin. And so a question might be, what would each point charge need to be, plus or minus, to have the electric field at the origin? And we can also ask, what would each point charge need to be, plus or minus, to have V equals 0 at the center or at the origin? So these are really interesting questions because remember that the potential is a scalar quantity. So if they're equidistant and they're the same charge, just one positive, one negative, in order for V to be 0 at the origin or the center, then I would just have to have an equal number of positive and negative charges. Doesn't matter where they are, or which ones are positive, which ones are negative, but I have to have an equal number of each. For the electric field, that one is a little trickier because electric field has a direction. It's a vector quantity. So in order to think about an electric field at the origin, I need to think about the direction the electric field is going to go from each of those positive or negative charges. And so now even thinking about, well, what if we want both 0? Is that possible? So let's find out. So let's look at an example. How do we set up the charges so that the electric field's going to be 0 and the potential is going to be 0? So in order for that electric potential to be 0, then I need an equal number of positives and negatives. And so for the electric potential to be 0, it doesn't matter where I put the two positives and where I put the two negatives. And I want to have the electric field to be 0 at that center point. Let's say this is positive and this is negative. Then I'm going to have electric field, remember, emanates from a positive and goes into a negative. And so it would do all kinds of things here. And if I made this one negative, I can imagine it's going to do all things here. And if this is negative and this is positive, again, I'm thinking of this, and I'm going to be doing these loopy things and going from this positive to this negative, right? I'm doing the same. So actually here is a configuration where I could have an electric field be 0 at the center and my potential is 0 as well. So let's do some more practice with that. So how would we set up the charges at points A, B, C, and D if we want the electric field to be 0 and the potential to be positive? So we want a potential that's positive, which means we need to have more positive charges than negatives. And that can happen either if we have 3 positives and 1 negative, or we can have all 4 positive. And if we do that at these locations, and the electric field is emanating out from these charges, right, then we're going to end up with 0 electric field at the center. So this would be the configuration if we want the electric field 0 and the potential to be positive. They just all have to be positive. If we want the electric field to point to the right and have the potential negative, if the potential is negative, that means either we have 3 negatives and 1 positive, or we have 4 negatives and no positives, but that would also give us an electric field of 0. So I'm going to have to go with 3 negatives and a positive, keeping in mind that an electric field wants to move from positive to negative. So if I want the electric field to point to the right, I'm thinking I want this scenario here. I want a positive at point B and a negative at point D, because that's going to have an electric field to the right. And I still need another positive and two more negatives to make the potential negative. So these are going to be negative. And so I'll have an electric field that goes this direction and this direction, but those vertical components of those electric fields will cancel each other. And so we'll end up with an electric field that points to the right. So now if I want the electric field pointing to the left and keeping the potential positive, it's very similar to that last example. I want the electric field to go to the left, so I'm going to need a negative here and a positive here. But if I want the potential to be positive, right, one thing I want to be careful of is mixing up this V with velocity. This is a capital V for potential. So here, if I have three charges that are positive and one's negative, I'll end up with positive potential. And my electric field is going to go from positive to negative. So what should we take away from this? Several things, right? The electric field is a vector, so that direction matters. And that the total electric field at a point is going to be the vector sum of the electric fields. Whereas electric potential is a scalar quantity. So the direction does not matter. Negative charges have negative potentials, positive charges have positive potentials. The total V at a point is the scalar sum of the potentials. And because of the relationship between E and V, we can have a location where E equals 0, but V does not have to be. But this also means that if V equals 0, then E has to equal 0. I hope that was helpful. Thank you and have a great rest of your day.